everywhere ice then? It's not like that?
No, sir. Just on the mountains. I live in a valley, so there is no ice, but the nearby mountains are covered completely.
Sorry. So we were here actually. So when you do actually any sort of the programming, or we were talking about this to solve using your this central difference in formula actually. And for that, if you have wrote that program for that based on this matrix, so I have a so I don't know how good you wrote the matrix run the program. This is what you are supposed to generate. So if I want to show you that what I wrote, so let's say this one here. So this is just to generate your first row only. Let's say I equal to 1. I have fixed it actually at I equal to 1. My first element is this because this is fixed. And I equal to n with the last row only. So this is your second last element. I hope so, right? This is the second last element 1 upon m square. Now, in between of this, from I equal to 2 to I equal to n minus 1, I am just generating everything by this command. This is, let's say, off diagonal of the right side. This is for the left side one. And diagonal one, you already know actually. So so this is just to generate your off diagonal elements, the left side one and right side one. By this command only. After that, if I want to just generate the main diagonal one, so I wrote this one more command here, a1ii means I equal to same means this is the main diagonal one, so I wrote by this way. Now after that we have your boundary condition matrix. So boundary condition matrix is given by this because you have only first element and only at the last element. So first row at b you can say 1 1. So this is minus t naught upon m square, and this b and 1, the last row is this one only. Once it is generated by these three commands, you can put the inverse, you can generate the matrix. Correct? So here, if I say I have taken, I think 500, the difference point here, this one. So based on that, I have calculated actually. So if for that only my solution actually, if I want to show you, so you can actually always solve your analytical one, calculate the error. So I calculated also error here also. So if you want to see the code also one by one. So this is here. So I started from here. You have here boundary condition, then both boundary, your length of the bar, initial coordinate at x naught, I have put this one. Then we have calculated m, the difference point between this. Thermal conductivity area, you have wrote this command just to generate your
Uh,
main diagonal
Excuse
elements,
me,
right?
sir. Sir,
Yeah.
the spatial difference, sir, shouldn't there be n plus 1 as the difference points are n?
Practically, let's say maybe I might have considered that the different page of let's say you have taken the entire length and you have divided into n number of points. So I will go up to let's say up to n minus 1. So then the time n would become your boundary.
Yes, sir. So
Okay.
then the matrix that will be generated would be n minus 1 cross n minus 1?
Yes, hope so.
Okay, sir.
So you have here, you are the generating here 1 to n here. So if you want to just generate here, so that you wrote for this is the between I equal to 2 to n minus 1 from here, and I equal to n, you are the last row only here. Okay.
Yes, sir.
So
Yes.
after that, what you have here, you have the generated again boundary condition matrix. Don't forget always to mention your comment box because it always helps. What are you doing in a particular segment of the program? Otherwise, you yourself would not be able to find what you did, let's say 1 year back or 2 years back, because just writing some variable didn't help you, right? So it's always keep on commenting that this section I did this much, this section I did this much, something like that. Then after that, your boundary condition, once you have the generated boundary, it is the easiest part now. T is inverse of A multiplied by B. That's all only, right? After that,
Yes, sir.
you have your analytical solution also. So analytical solution, you have the generated from here, the something like that. And after that, you got analytical temperature from here. Based on analytical also, you have calculated your error actually, the percentage error. This is T calculated by your program previously. This is T calculated by analytical one divided by analytical one. You have calculated percentage error here. Okay. After that,
Yes, sir.
you plot it here, that X length of this and B, and the same graph you have plotted your analytical one. This is your the numerical solution. Analytical solution, you give black color with dotted points. You can change this color, maybe red, green, yellow, whatever you feel comfortable. You can write here whatever you want, star, circle, something like that. And then hold on. So hold on command will help it keep on plotting on the same graph actually. After that, this is something labeling command, because you need not to do anything editing manually. So in MATLAB, you have everything how to label your graph automatically. You need not to do anything by hand later on. So you have every command there. So you want to put the X label here distance, and which is in terms of meter. You want to make it font size 20, and you want to make the font bold actually. So that's the this command here. So that would help you. The everything would come automatically. Later on also you can edit it, but it's better if you can write here. Then you have calculated heat transfer rate again, the difference in heat transfer rate, again plotted the thing, the same command for you gave for that one also. After that, once you do all this part, you got this particular graph for temperature. So here you cannot, because if you see the graph and your data are very consistent, if you will zoom it, you will find the difference. But here you say the 50 to 120, they are very close points or very compact. So you cannot find what is the difference here, right? You will find, means everything is perfect, correct or not?
Yes.
Yes, sir.
So for that, your error calculation would help. So if you will do your error calculation here, so this is what from here you will come to know. Yes, there are the differences here, and we were talking here. So let's say you have starting initially, let's say for let's say 20 points something, you got some error. Don't change the graph, nothing like that. Only thing you just make 20 to 50 only. That next graph would also come here also. So let's say this first graph maybe for that 20, your error graph may be somewhere here, because it would be a very high error at that particular point. So it would be here. 50, it would something that decrease, 100 further decrease, 200 further decrease, 500 further the decrease. And let's say you want to make it 500 to 1000. At the same time, you also count your CPU time, because these are the analysis need to be taken care while you are presenting your work to publish in some computational journal. People always ask that what is your computational, how are you comparing the two? So each time you are taking a difference point, your maximum error. After that, you are adding the error also. Cumulative absolute means the error. You are not interested only error at one particular point. You are adding what is my total cumulative error, and that need to be minimized actually. Okay, so in that case, you have to add the error from here to here, entire error from here to here. So that is the total sum of the error actually. So that need to be taken care, not at the error at 1 point. Okay, 1 point I got 0.005. I am happy. No, it's not that way. So each time you calculate total error at all the points and keep on adding at the same column. One column you make for time, computational time or the CPU time, and then you make the comparative statement that if I am going to this time, my error is just getting decreased by this value. However, my computational time is tremendously increasing. So therefore, I am stopping at this particular point because I don't find this computationally justified. Okay. So this is the way you have to always actually means justified your number of the difference point in any computational technique. Fine.
Sir,
Yeah.
so the cumulative error is found out by simply adding error at different points?
Yes, yes, yes. Just add the error at all the point without any sign. Don't add plus minus. Absolute error actually.
Okay, sir.
Because error is error. No matter whether it's lower than analytical or higher than analytical, it's the error both the way, right? So if you add with sign, you may come up with the zero, but that's not true, right? Because some would be minus, some would be plus, and if you will add them with sign, you would be very much happy that my total error is zero, but it's not the case. So you have to always add the absolute error actually.
Okay, sir.
Okay. Yeah. Now, once it is done, so let's, which I was talking in the yesterday's class, let's to change our program or our formulation for convective boundary condition. We have talked previously only for temperature boundary condition. Now we want to change that the previous formulation just for your convective boundary conditions. So as I told you the yesterday actually, so your convective flux, heat flux is given by this. Let's say both the ends of the bar you are maintaining at some flux, and how are you maintaining that we don't know, either by heating or by the solar flux or some other flux you are getting that somehow. Just like a actually in case of a heater, let's say you are talking about the means ironing actually, iron actually, so in that case you have a heating coil there, right? So in that case of the heating coil, you are always providing some heat input, correct? So let's say you are
Yes,
providing
sir.
heat input 50 watt by the heater. So you know the heating capacity of the heater. You know the total area of that particular press actually. So iron base, so you know the area. So that Q by A would be your flux actually, because there's no other way to measure the temperature of that base plate from inside. So that way you know the flux, or some way, let's say you are burning in a deformer, or let's say your furnaces in the plant. So in that particular place also there no way to measure the heat transfer coefficient at that particular point also. So you know the how much fuel you are burning, you know the temperature, actually calorific value, and most of the time you are considering, let's say, completely insulated part, because you are burning inside the furnace, so no heat is going waste. Everything will go to the wall of the furnace only, correct or not? So that way you can consider
Yes,
that
sir.
the zero wave type of condition, or in case of temperature, you can put a, let's say these days you have a thermocouples or radiation pyrometers and also there so as to measure the temperature. So depending on that, let's say you have flux boundary condition. So flux boundary conditions are given by that. So you have to balance by your convective flux is going to have your convection flux. So whatever flux is coming, same thing is going out. So based on that, you are calculating here. So this is the flux balance at your the left boundary. This is flux balance at the right boundary, and you need to discretize here. Okay. You need to discretize these conditions as we talked in the last class here. I can show that slide I wrote somewhere here, I think. So this is the like that here. So if you want to write at x equal to this, so this is your, So after means adjusting this one, you got this T naught equal to T surrounding K plus Ti plus 1 upon 2 delta XH, right?
Yes, sir.
Correct. So same thing I did here. So if I want to show here, so this one, so if you will keep on doing it, adjusting this, so you will get this expression for your T naught, this expression for your last one, actually the Tn plus 1. Okay. And I hope I did this adjustment also somewhere here. Yeah, this one here. So this you have taken your first derivative of your dt upon dx. You have here k also, so you have here minus k dt upon dx, right? So for that you wrote the central difference formula here. So you brought the k here, so you wrote in this way, and after that you just put I equal to 1 here, so you got T naught, so you got the expression while the rearranging this, you got the T naught expression is this. T2 upon this and this one. Fine. Now you already know at in the previous with the formulation you have somewhere is T naught. So at the place of T naught you have to substitute this one only. Out of this your T2 is unknown temperature. T1 is known to you because this is the atmospheric temperature from where you are maintaining a convective flux, right? Correct?
Yes, sir.
Yes.
Now at
Yes,
the
sir.
last boundary also you have the maintaining flux here again. So for that particular part you wrote I equal to n here, and then you are again discretizing here. Make sure this don't change the direction from your side and all this. See here, you are just considering that this heat is going from your rod to atmosphere. Fine.
Yes, sir.
Yes, sir.
So that's what you did here, and after that you arranged it, and then you got this expression for your Tn plus 1 would be this temperature, the last temperature, and that boundary temperature here, surrounding temperature, sorry. So now you got here, and after the substituting your first equation, if you write your first equation, what you have there, here you have T2, here you have T1, here you have complete your T naught, right? This is what your T naught was. If you write,
Yes, sir.
correct? So at the place of T naught, I just substituted the expression of T naught, which I got my convective boundary condition. Now I can rearrange it. So if I rearrange it, so I will get this one here. So I kept the unknown temperature to the left hand side and known temperature to the right hand side. Okay.
Yes, sir.
Yes, sir.
Same thing I did for Tn plus 1 thing. So for that, again, I go bend back my equation number 5, substituted there here. So there, this was the expression for your Tn plus 1. And this is you have here. Now rearrange it here. So you got Tn minus 1, Tn, and this is your boundary size. So this is known, whatever known will go to the boundary matrix. Whatever is known will go to the unknown temperature matrix again. So only your first and last equation has been changed. Rest of the equations are same. Correct or not?
Yes, sir.
So for that, if you will see your matrix, so your matrix would look like again this. Your A matrix would be your first row has been changed only at this particular place, and last row at this particular place. Rest of the body of the matrix is same as you have previously. Fine. So you can use the same code with just slight change only at this A12 value, and this is a n minus 1, a n comma n minus 1 here, right? Only these two change. So if you will do that, and this is your boundary condition matrix. Now only your first element has become this, and last element has become this one, right?
Yes, sir.
Fine. So for that case, uh, again you can write your MATLAB code for the same thing. So there are no change here. Only thing here, the second element of first row has been changed by this particular formula only here. Here, body, rest of the body from 2 to n minus 1 is same. And the last one here, again, you have changed this one. This is your boundary conditions of matrix. You wrote only first element and last element. Rest of the terms are the zero, so you need not to write anything for them. So if you'll do that particular part here, then your matrix, your program would be completed here. Now, this, I wrote the code first. We have the problem statement later on here. So you have, I changed here slightly. Your x is 0.5. Thermal conductivity, I have taken 2.3 here. Area is 20. And left side convective heat transfer coefficient is 30. And this is actually temperature of this. I am not. This is the temperature of the surrounding atmosphere gas on the left side. This is on the right side one, and this is the right side convective transfer coefficient. Because you may not have same type of heating medium or gases or environment of on both the ends. Fine, correct.
Yes, sir.
And this
Yes,
is
sir.
if you have the some confusion that how to take unknown points and all this. This is also the one of the way to actually generate your the length vector here. So you take n divided by this one here. You got the difference point, and this is your x matrix here. X0, you are taking that much difference point m, and keep on adding that until you get the last n. So sometimes, let's say you people are getting confusion kitna points chahiye, right? So in that case, let's say you know the L, right? Correct or not? So either
Yes.
you calculate by this way, or you just fix up your M and just use this particular command here. It will automatically generate the number of difference points. Total points actually, not only the difference point. Total points from starting to end. Correct?
Yes, sir.
Yes, sir.
Okay. So then you are just fixing your flux boundary conditions. So I wrote here flux boundary condition in terms of formula also, so that I should know, okay, whatever I am doing is correct or not. I was just talking in the program to you this one. You are maintaining conductive flux. You are maintaining a direction of flow. So your direction of flow, you are maintaining of heat from left to right, so positive axis direction. So therefore, you wrote this is the Fourier's law of conduction there, and from here HA2. Here you wrote TL minus TA2 from bar to atmosphere. You are not saying that heat is coming from that way. No, you are balancing in a particular site. So there, that need to be taken care here, right? So, and then you wrote your body of the rest of the program here. So you the generated here. This is also the one of the command. Let's say initially you want to assign 0, 0 for matrix A, matrix B. So this is also the one of the command that fix up the zeros. If you won't fix up the zeros, also it will automatically do also that particular part. So that's not a big deal actually. Then you wrote the same thing here. This is the same program. Only thing you have changed only this particular equation here again. This is your boundary condition. The body one, I equal to 2 to n minus 1. Same thing. And then you have last one here. Okay.
Yes, sir.
So after doing this, and then you have solution, then you have solve it here, and after that you write it here and plot it here, same thing. So plot command. Then you have calculated this, and after that again you are balancing by your analytical solution also. So what is coming my temperature using my analytical solution also, because I have to also compare my solution from analytical as far as I can get the analytical one. Some problem are really impossible to solve is analytically by general engineers, so they don't go for that. Actually, most of the time people write a program, and sometimes analytical solution is not this available, or let's say very tedious. People don't solve it, or what they want to do, they want to correlate the program solution by our experimental thing and keep on the defining. Logically, they want to say that if they did everything well, so that program is also not validated by anything but validated by experimental data. So that is also one way, and you can also cross-check your program from earlier published the data also. Some that too from a uh, reputed source, not a, just like that you took the any program of anyone, and if that person might have made wrong and you might have done something correct, so you might be means scratching your head or what wrong I did, because you did correct and that person did wrong. Yes or no?
Yes,
So
sir.
it also
Yes, sir.
happens. So whenever we want to validate our computational or data, best way is that validate from our own means analytical solution if possible. Not possible, then if the somebody else solve same type of problem, so we can solve it. This is just to taken care in case of simulation study part. Rest of the part, if that is also not means available, that you don't have anything, so only thing you will justify your analysis based on the prediction here, that whatever is predicting is making some sense, or that's why you are considering that whatever you wrote is also correct also. Okay. So once you did this part, then this was the problem statement for this, that the large plane wall of length 0.4 meter, thermal conductivity 2.3 watt per meter per degree Celsius, surface area is given 20, temperature and convective heat transfer coefficient of gas and left sides are given this one, 80 degree and 30 watt. Right side is 15 degree and 24 watt, and assuming constant thermal conductivity, no heat generation within the wall, obtain steady state temperature distribution in wall and heat transfer rate through the wall. So this was your problem statement. Code we have shown for that previously, and this is what analytical solution. I hope you will get the analytical solution. You would be able to get the equation for analytical solution, right?
Yes, sir.
आ जाएगा ये equation number 8 or 9. If you got 8, you will get 9 easily also.
So we will,
Yes,
So,
sir.
huh?
so we will try solving it.
Yes, yes, you try it. If you don't get it, please let me know. Then it's just the integration of that. You are balancing the flux, integrate that, and solve it only. So this is your analytical solution, and let's compare them. What are we getting here? So this is I just found here error analysis, that that's way you did it. Because this work we have published in international, that journal of computer means chemical engineering and technology by the Valley publication. So we wrote everything error analysis and all this. So you say the absolute means error was 10 to the power minus 13. So this was the minus 13, and if you will change it from the, let's say, 20 difference point, this is for this one, and comparison time needed by this 30 seconds. So this way you are just justifying your points actually. Okay. So this is how you will say the temperature by you are not finding here any change also. Everything looks very nice. So it means your but if you will see error graph. I forgot to paste here actually. So I am not here at that time being. So I can show you in my paper also that time. So this is what you have. Now we did actually two type of the problem. Generally we have only two type. Either you have temperature boundary condition or flux boundary condition, right? So we have taken two distinct type of condition, that either temperature or either flux. Now you can mix them up. So either you can have one side in temperature, other side in flux. So you should take care of that part where you have flux one. Just it will just add up to you the something to get the that boundary temperature in terms of flux boundary conditions. Substitute that, and you can write a separate program for that by just changing a simple program means command for that. So once you wrote for one case, it's not tough for other case. Fine.
Yes, sir.
Now, do you have any doubt in this before I will go to this for the c- cylindrical coordinate? So if you have anything to that, you can ask. Otherwise, we can go for this one.
So no doubt yet. We'll try it once, and then if we'll have any doubt, we'll ask you tomorrow.
Yeah. 1 minute, okay. Everybody are able to write the program or not? Are I, Sabika?
Yes, sir.